So from our earlier discussions, hopefully you've recognized that the scientific method is heavily dependent on observation and experimentation. And both of those things are going to involve making measurements. So we should talk a little bit about the qualities of good measurements. So all measurements have to have at least two components. They need a number that tells us how big our measurement is. That's often referred to as the magnitude of the measurement. And they need units, which are a label that tell you what is being measured. Now, often our measurement won't make a lot of sense unless we include some other information as well. So for example, if I'm trying to describe where I live, I might say I live 40 miles north of Pierce College, Puyallup. And if I didn't include the direction north, that measurement wouldn't make a lot of sense. Similarly, so if I was trying to describe where I had driven and I said I drove at 30 miles per hour, without adding the direction east, that measurement wouldn't be particularly useful. Often we'll include some kind of measurement or an estimate of the uncertainty in our measurement. So if I write something like today's maximum temperature was 27.5 plus or minus 0.2 degrees Celsius, what I'm really saying is that the daily maximum temperature was somewhere between 27.3 and 27.7 degrees Celsius. So somewhere in there was the true maximum temperature for that particular day. Okay, so this number here indicated by the plus or minus notation is the uncertainty. Now, in chemistry, we use the International System of Units, which is the modern version of the metric system. This was developed in France, and in French, this is referred to as Système International. So you'll often hear people talking about SI units because they are using the French abbreviation. Now, we don't use this in the US in our daily lives widely, but it's it is the system of units that are used by professional scientists and engineers. So you'll get used to using it. You will need to be able to use conversion factors and formulas to transfer measurements between different systems of units. And there have been a lot of folks who have got into trouble doing this, and it's often kind of quite disastrous if this happens, and if nothing else, it can be extremely embarrassing. So a good example of where confusion between systems of units has caused an issue was with Air Canada Flight 143. And what happened here was the confusion between pounds, of which there are 2.2 pounds, and kilograms. And the ground crew had loaded on fuel that had been weighed out as pounds, but they had recorded it as kilograms, so they'd actually communicated to the flight crew that the plane contained twice as much fuel as what it did. And what actually happened was that the plane basically ran out of gas mid-flight. It hit half a tank, and everything stopped working. So yeah, that's a good example here. Now, this plane is often referred to as the Gimli Glider. The pilots were quite smart. They had a memory of there being an Air Force base near where they had run out of fuel that was called Gimli Air Force Base. What they didn't know is that it had been converted into a racetrack, so they were able to glide the plane in. They couldn't get all of the landing gear down, and what they didn't know was that there actually were people who were using the runway as a racetrack. So very, very, very close to killing a bunch of people. Fortunately, no one was seriously hurt in this incident. Now, something else that happened was that there was a confusion between NASA and one of its contractors, and as a result, the Mars Climate Orbiter didn't orbit. The Mars Climate Orbiter became the Mars Climate Keep On Flying, and they lost a couple of $100 million worth of spacecraft. Now, of course, there was a big investigation, and everybody knows who made the error. So you don't want to be that guy, right? So yeah, it's really, really important. On a sort of more serious note, it's estimated that approximately 56 million errors are made by pharmacists every year in the dispensing of medications. So it's really easy to do. You know, it's not like these people that are making these mistakes are stupid. You know, these things happen when we aren't careful, when we're tired, when we're grouchy, when we're distracted. So, you know, as professional, you know, as STEM professionals, whether that be as an engineer, a scientist, or a healthcare provider, we need to be really, really cautious not to make mistakes in our measurements, because it can get bad real quick. Okay, so as I said, we use the SI system of units, and the SI system of units has what we call 7 base units. And so their names and abbreviations are given below. So we have a length, mass, time, and they have the length, the base unit is the meter. For mass, it is the kilogram, and for time, it is the second. These ones are really, really commonly used in chemistry. As well as a name, every base unit has a symbol. So we have lowercase m for length, lowercase kg for mass, and lowercase s for second. Generally, if the unit isn't named after a person, or always if the unit isn't named after a person, it's given a lowercase abbreviation. Temperature, the base unit is Kelvin, and the symbol of the unit is an uppercase K because it's named after Lord Kelvin. We will often measure temperature in degrees Celsius, but typically when we're using measurements of temperature in formulas, we almost always use Kelvin. Later on in Chemistry 163, we'll be looking at electric current. Electric current has the base unit of the ampere, named after Professor Ampere, so it gets an uppercase A. Amount of substance, the base unit is the mole, and the symbol, the abbreviation for the mole is MOL. And luminous intensity, the base unit is the candela, and it has an abbreviation CD. Now, I can't recall ever encountering the candela in general chemistry. Now, it is important to recognize that obviously we can measure many, many more things than more than 7 things. But what we do is we combine these base units to create what are called derived SI units. So it could be something so simple as density. Density is mass over volume. And you'll see that there is a base unit for mass, but there isn't a base unit for volume. So volume has units of length cubed. So the base unit for volume would be the meter cubed. So density would end up with units of kilograms per meter cubed if we were in the base units. Now, some of these derived units are, have quite complex units. They're like quite elaborate combinations of the different units. So 2 that we're going to use fairly quickly, we're going to be using them in Alex almost immediately, and then we're definitely going to be using them from week 2 onwards, are the joule, and 1 joule is equal to 1 kilogram meters squared per second squared, and also the Pascal, which is a unit of pressure, and that's equal to 1 kilogram per meter per second squared. And notice that what you're going to be seeing a lot of is people using the notation of x to the minus n interchangeably with 1 on x to the n. So if I look at the units for pascals there, you can see it's written with negative exponents. So this is kilograms, meters to the minus 1, seconds to the minus 2. But it's important to realize that that also might be written as kilogram meters to the 1 second squared. So realizing that those 2 things are equivalent is important, and you might choose to use one over the other depending on the circumstances. Often we'll use this form to make when we're cancelling units to kind of make dimensional analysis easier. but it's a little more difficult to enter that into the computer because it has the fraction there. So if you're entering it into the computer, you might use this form. Now, chemists, we talked about chemists working with things in the macroscopic domain and also in the microscopic domain. So we'll often deal with very large numbers alongside very small numbers. So to help us do that, we've developed a system of what I refer to as decimal prefixes. So what decimal prefixes are shorthand abbreviated forms of writing that the number needs to be multiplied by a power of 10. So every decimal prefix has a name, and then it has an abbreviation for that particular prefix. So we have mega, which has the abbreviation uppercase M, and that means multiply by 10 to the 6. So if I have 1 megajoule, that means 1 times 10 to the 6 joules. You see the M there just means do that. All right. Or if I have 1.6 megajoules, then that would mean 1.6 by 10 to the 6 joules. So it's just a shorthand for expressing that we want the number to be multiplied by a power of 10. So we have a kilo, which is a lowercase k, and that means multiply by 10 to the 3. We have deci, which is a lowercase d, and that means multiplied by 10 to the 1, or you could think of that as 0.1, because like this you could think of as 1,000, this you could think of as a million. Centi means multiply by 10 to the minus 2, and the abbreviation there is a lowercase c. 10 to the minus 2 is the same as 0.01. Milli has abbreviation lowercase m, and that means multiplied by 10 to the 3, or 10 to the minus 3, which is 0.001. And then micro, that has the abbreviation mu, so I should write that out, mu. It's a Greek letter, looks like a little U where you make the front of it a bit longer, and that means multiply by 10 to the minus 6. So there are 6 prefixes here, and I would like you to know their names, abbreviations, and meanings. So you need to memorize what's in the table there. Now, it's worth pointing out that there are a lot of decimal prefixes, but I only want you to memorize those 6 because they are the ones that appear in standardized exams of general chemistry. Your book has a big table of them. I think it's like it comes immediately after the table of the SI base units. It's pretty easy to find, so you might want to have that open in a tab when you're answering questions concerning decimal prefixes. There are a couple of things that you can, little tricks you can use to help you memorize those 6. Centi, just like cents in the dollar, you get 100 cents in the dollar, you get 100 centimeters in the meter. Deci, think of it, it begins with D. And just like there are 10 dimes in a dollar, there are 10 decimeters in a meter. And then kilo, you probably, if someone told you, that you were going to earn 1K, you would understand that that meant that you were going to earn $1,000. And similarly, you might have seen abbreviations like this when people are talking about things like the state budget or something, and you would understand that 1 uppercase M meant 1 million, in this case, dollars. So, you can remember a few of them fairly easily. We've got 1, 2, 3, 4 of them, just by thinking about how we talk about currency. Okay, let's move on. So, we've talked about the basics of measurements. We've talked about the fact that we're going to use the SI system, the International System of Units, which has 7 base units, which are then combined to form, almost endless derived units. There's a Wikipedia article on SI derived units that has a whole bunch of them written out in the abbreviated form and in the longer form. You might find that useful to have that as a resource when you're doing a test or your ALEX objectives or something like that. And then the other thing to keep in mind is that within the the SI system, we're going to use decimal prefixes to take the place of multiplying by powers of 10. You need to know the 6 of those that I identified, but you also need to understand that there's an extensive number of them, and you can look those up in your book as needed.